Hello and welcome to Morehouse's Math Menagerie. Today we're going to be talking about two sample...
Hey Jared, dinner's ready.
Mom, I told you not to come in the basement when I'm filming for my class.
Well, I made your favorite. It's spaghetti tonight.
Ooh, spaghetti. Welcome back to Morehouse's Math Menagerie. Today we're going to talk about two sample significance tests with paired data. Let's go to the PowerPoint.
Okay, the problem we're going to be dealing with today is Mr. Morehouse is curious about the number of absences students have in each class. He is suspicious that students tend to be absent from class more during the second semester than the first. In order to investigate this issue, he took a random sample of students from his AB Stats courses and recorded the number of absences they had in each semester. He wants to conduct a significance test at the alpha equals 0.1 level to determine if his suspicion is correct. This table shows the data that was collected by Mr. Morehouse. He has the number of absences for each semester for a randomly selected group of students. Now, since the number of absences in each semester is not independent, it came from the same student, we cannot do a two-sample test on this data. Instead, what we're going to do is we're going to find the difference in the number of absences in each semester and use that as our data for the test. Since Mr. Morehouse was suspicious that there were more absences in the second semester than the first, we found our difference by taking semester 2 and subtracting semester 1. For step 1, we're going to define our parameter as mu sub d, the mean difference between students' absences in semester 1 and semester 2. Our hypotheses for the null will be that mu sub d equals 0, and our alternative is that mu sub d is greater than 0. And we believe it's greater than 0 because if there are more absences in second semester, then that difference should be positive. Step 2 are conditions. A random sample was stated in the problem. For independence, 10 times 16 is 160, which is less than the population. To show normality here, we're going to look at the box plot. You can see there's no extreme skewness, nor are there any outliers. So a t-test is appropriate for this data. And while we're on the subject of graphs, I thought I'd show you this one. All right, calculations by hand. The mean of our differences here for the sample was 2.25 with a standard deviation for our sample of 3.1937. We have an n of 16. If we plug that into our test statistic formula t, we end up with a 2.818 as our test statistic. Degrees of freedom here are calculated as normal with n minus 1 being 15. We can take this data and go to the t-table and look up our p-value. By calculator, we can just run a t-test. This is not a two-sample t-test since we're only running it on the differences. If we plug in our data into the t-test, we find out the same t, 2.818, and a p-value of 0.006. Here is a graph of our test, just showing you a visual of what we calculated. We found that our test statistic was 2.818, and the area to the right of that is the 0.0065. In conclusion, the p-value of 0.0065 is less than alpha of 0.1. Thus, we reject the null hypothesis in favor of the alternative hypothesis. There is sufficient evidence to suggest that the true mean difference between students' absences in semester 2 and semester 1 is greater than 0. I will leave you with this comic. Thanks for joining us and have a great day.